TCP is a reliable layer 4 protocol. TCP uses a three-way handshake to create reliable connections across the network. TCP can reorder segments that arrive out of order and retransmit missing segments. UDP is a simpler and faster cousin to TCP. UDP is commonly used for applications that are lossy or can handle some packet loss, such as streaming audio and video. It is also used for query response applications, such as DNS queries. Secure Shell, or SSH, was designed as a secured replacement for Telnet, FTP, and the Unix R commands. It provides confidentiality, integrity, and secure authentication, among other features. SSH includes SFTP and SCP for transferring files. SSH can also be used to securely tunnel other protocols such as HTTP. SSH servers listen on TCP port 22 by default. FTP is the file transfer protocol used to transfer files to and from servers. Like Telnet, FTP has no confidentiality or integrity and should not be used to transfer sensitive data over insecure channels. FTP uses two ports. The control connection, where commands are sent, is TCP port 21. Active FTP uses a data connection, where data is transferred that originates from TCP port 20. DNS is the domain name system, a distributed global database that translates names to IP addresses and vice versa. DNS uses both TCP and UDP. Small responses use UDP port 53, while large responses, including zone transfers, use TCP port 53. The TCP IP model is a popular network model created by DARPA in the 1970s. TCP IP is an informal name named after the first two protocols created. The formal name is the Internet Protocol Suite. The TCP IP model is simpler than the OSI model. While TCP and IP receive top billing, TCP IP is actually a suite of protocols including UDP and ICMP, among many others. The internet layer of the TCP IP model aligns with layer 3, or the network layer, of the OSI model. This is where IP addresses and routing live. When data is transmitted from a node to one LAN to a node on a different LAN, the internet layer is used. IP version 4, IP version 6, ICMP, and routing protocols, among others, are internet layer TCP IP protocols. IP version 6 is the successor to IP version 4, featuring far larger address space, simpler routing, and simpler address assignment. A lack of IP version 4 addresses was the primary factor that led to the creation of IP version 6. Though most modern systems now are dual stack and use both IP version 4 and IP version 6 simultaneously. Hosts may also access IP version 6 networks via IP version 4. This is called tunneling. Internet Control Message Protocol, or ICMP, is a helper protocol that assists layer 3. ICMP is used to troubleshoot and report error conditions. Without ICMP to help, IP would fail when faced with routing loops, ports, hosts, or networks that are down. ICMP has no concept of ports as TCP and UDP do, but instead uses types and codes. Telnet provides terminal emulation over a network. Terminal means text-based VT100 style terminal access. Telnet servers listen on TCP port 23. Telnet was the standard way to access an interactive command shell over a network for over 20 years. Telnet is weak because it provides no confidentiality. All data transmitted during a Telnet session is plain text, including the username and password used to authenticate the system. The network access layer of the TCP IP model combines layer 1 and layer 2 of the OSI model. It describes layer 1 issues such as energy, bits, and the medium used to carry them, copper, fiber, wireless, etc. It also describes layer 2 issues like converting bits into protocol units such as Ethernet frames, MAC addresses, and network interface cards. IPv4 is Internet Protocol version 4, commonly called just IP. It is a simple protocol designed to carry data across networks. It is so simple that it requires a helper protocol called ICMP. IP is connectionless and unreliable. It provides best effort delivery of packets. If connections or reliability are required, they must be provided by a higher level protocol carried by IP such as TCP. IP version 4 uses 32-bit source and destination addresses usually shown in dotted quad format, such as 192.168.2.4. A 32-bit address field allows 2 to the 32nd, or nearly 4.3 billion addresses. TCP connects from a source port to a destination port, such as from source port 51,178 to destination port 22. The TCP port field is 16 bits, allowing port numbers from 0 to 65,535. There are two types of ports, reserved and ephemeral. A reserved port is 1023 or lower. Ephemeral ports are from 1024 to 65,535. Most operating systems require superuser privileges to be able to open a reserved port. Any user may open an unused ephemeral port. A MAC address is the unique hardware address of an Ethernet NIC, typically burned in at the factory. MAC addresses may be changed in software. Historically, MAC addresses were 48 bits long. The first 24 bits form the organizationally unique identifier, also known as the OUI, and the last 24 bits form a serial number, formerly called an extension identifier. The IEEE created the EUI-64, also known as the Extended Unique Identifier, for standard 64-bit MAC addresses. The OUI is still 24 bits, but the serial number is 40 bits. This allows for far more MAC addresses compared to the 48-bit addresses. IP version 6 auto configuration is compatible with both these types of MAC addresses. Hypertext Transfer Protocol, or HTTP, transfers unencrypted web-based data. HTTPS, or Hypertext Transfer Protocol Secure, transfers encrypted web-based data via SSL TLS. HTTP uses TCP port 80 and HTTPS uses TCP port 443. HTML, or Hypertext Markup Language, is used to display web content. The host-to-host transport layer, or more commonly called simply the transport layer, connects the internet layer to the application layer. It is where applications are addressed on a network via ports. TCP and UDP are the two transport layer protocols used in TCP/IP. A bus network topology connects each system to a trunk or backbone cable. All systems on the bus can transmit data simultaneously, which can result in collisions. A collision occurs when two systems transmit data at the same time. The signals interfere with each other. Ethernet is an example of a bus network. The TCP/IP application layer combines the session, presentation, and application layers of the OSI model. Most of these protocols use a client-server architecture where a client connects to a listening server, such as SSHD. The clients and servers use either TCP or UDP, or sometimes both, as a transport layer protocol. TCP/IP application layer protocols include Secure Shell, Telnet, FTP, and many others. SMTP is the Simple Mail Transfer Protocol, which is used to transfer email between servers. SMTP servers listen on TCP port 25. POP version 3, also known as Post Office Protocol, and IMAP, also known as Internet Message Access Protocol, are used for client-server email access, which use TCP ports 110 and 143 respectively. So next, let's go over standard network topologies. A star network topology employs a centralized connection device. It can simply be a hub or switch. Each system is connected to the central hub by a dedicated segment. A mesh network topology connects systems to all other systems using numerous paths. A partial mesh topology connects many systems to many other systems. A mesh network topology provides redundant connections to systems, allowing multiple segment failures without seriously affecting connectivity. A ring network topology connects each system as points on a circle. The connection medium acts as a unidirectional transmission loop. Only one system can transmit data at a time. Traffic management is performed by a token. A multitude of protocols exist at the TCP/IP application layer, which combines the session, presentation, and application layers of the OSI model. The OSI model, or the Open Systems Interconnection Model, is a conceptual framework used to describe the functions of a networking system. The OSI model characterizes computing functions into a universal set of rules and requirements in order to support interoperability between different products and software. In the OSI reference model, the communications between a computer system are split into 7 different abstraction layers. These layers include the physical layer, the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and the application layer. The OSI model was created at a time when network computing was in its infancy. It was published in 1984 by the ISO, and though it does not always map directly to specific systems, the OSI model is still used to this day as means to describe network architecture. So the first layer we'll look at is the physical layer. The physical layer is the lowest layer of the OSI model, and it is concerned with electrically and optically transmitting raw and structured data bits across the network from the physical layer of the sending device to the physical layer of the receiving device. It can include specifications such as voltages, pin layout, cabling, and radio frequencies. At the physical layer, one might find physical resources such as network hubs, cabling, repeaters, network adapters, or modems. The second layer of the OSI model is the data link layer. At the data link layer, directly connected nodes are used to perform node-to-node data transfer where the data is packaged into frames. The data link layer also corrects errors that may have occurred at the physical layer. The data link layer encompasses 2 sublayers of its own. The first, immediate access control, also known as MAC address, provides flow control and multiplexing for device transmissions over a network. The second, the logical link control, also known as LLC, provides flow and error control over the physical medium as well as the identifies line protocols. The third layer of the OSI model is the network layer. The network layer is responsible for receiving frames from the data link layer and delivering them to their intended destinations based on the addresses contained inside the frame. The network layer finds the destination by using logical addresses such as IP addresses or internet protocol. At this layer, routers are crucial components used to quite literally route information from where it needs to go between networks. The fourth layer of the OSI model is the transport layer. The transport layer manages the delivery and error checking of data packets. It regulates the size, sequencing, and ultimately the transfer of data between systems and hosts. One of the most common examples of the transport layer is TCP, or the Transmission Control Protocol. The fifth layer of the OSI model is the session layer. The session layer controls the conversations between different computers. A session or connection between machines is set up and managed at layer 5. Session layers services also include authentication and reconnections. The sixth layer is the presentation layer. The presentation layer formats or translates data for the application layer based on syntax or semantics that the application accepts. Because of this, it is at times also called the syntax layer. This layer can also handle the encryption and decryption required by the application layer. The seventh layer is the application layer. At this layer, both the end user and the application layer interact directly with the software application. This layer sees network services provided to end user applications such as web browsers or Office 365. The application layer identifies communication partners, resource availability, and synchronizes communication. So next, let's look at common network devices. Network devices include firewalls, switches, routers, and gateways. Firewalls are essential tools in managing and controlling traffic. A firewall is a network device used to filter traffic. Switches repeat traffic only out of the port at which the destination is known to exist. Switches offer greatest efficiency for traffic delivery, create separate collision domains, and improve the overall throughput of data. They usually occur on the OSI model layer too. Routers are used to control traffic flow on networks and are often used to connect similar networks and traffic flow between the two. They can function using statically defined routing tables, or they can employ a dynamic routing system. They occur on layer 3. A gateway connects networks that are used differently for network protocols. They're also known as protocol translators. Can be standalone hardware devices or a software device. Network gateways also work at layer 3. Some other common network devices are repeaters, concentrators, amplifiers, bridges, hubs, and LAN extenders. Repeaters, concentrators, and amplifiers are used to strengthen the communication signal over a cable segment, as well as connect network segments that use the same protocol. These all take place at layer 1. Bridges are used to connect two networks, even networks of different topologies, cabling types, and speeds, in order to connect network segments that use the same protocol. Bridges take place at layer 2. Hubs were used to connect multiple systems and connect network segments that use the same protocol. A hub is a multi-port repeater. Hubs operate at OSI layer 1. LAN extenders are a remote access multi-layer switch used to connect distant networks over a WAN link. Network devices include LAN and WAN technologies, also known as local area network technologies and wide area network technologies. WAN connections and communication links can include private circuit technologies and packet switching technologies. Private circuit technologies use dedicated physical circuits. Private circuit technologies also use dedicated or leased lines, PPP or point-to-point protocol, SLIP or serial line internet protocol, ISDN or integrated services digital network, and DSL, which stands for digital subscriber line. Packet switching technologies use virtual circuits instead of dedicated physical circuits. This is more efficient and cost-effective. Packet switching technologies include X.25 frame relay, asynchronous transfer mode, also known as ATM, synchronous data link control, also known as SDLC, and high-level data link control, also known as HDLC. So next, let's go over the types of firewalls. These include static packet filtering firewalls, application-level gateway firewalls, and circuit-level gateway firewalls. Static packet filtering firewalls filter traffic by examining data from a message header. Application-level gateway firewalls use a mechanism that copies packets from one network into another. They then change the source and destination addresses to protect identity of internal or private networks. Circuit-level gateway firewalls are used to establish communication sessions between trusted partners. They operate at the session layer, or layer 5 of the OSI model. Some other types of firewalls include stateful inspection firewalls, deep packet inspection firewalls, and next-generation firewalls. Stateful inspection firewalls evaluate the state or the context of network traffic. Deep packet inspection firewalls use a filtering mechanism that operates typically at the application layer in order to filter the payload contents of a communication rather than only on the header values. Next-generation firewalls is a multifunction device composed of several security features in addition to a firewall. These include IDS, IPS, TLS SSL proxies, web filtering, QoS MGMT, bandwidth throttling, NAT, VPN anchoring, and antiviruses. Next, let's talk the difference between stateless and stateful firewalls. Stateless firewalls watch network traffic and restrict or block packets based on source and destination addresses or other static values. They are not aware of traffic patterns or data flows. They also typically are faster and perform better under heavier traffic loads. Stateful firewalls can watch traffic streams from end to end. They are aware of communication paths and can implement various IP security functions such as tunnels and encryption. They are also better at identifying unauthorized and/or forged communications. Next, let's talk intrusion detection systems and intrusion prevention systems. Intrusion detection systems analyze whole packets, both header and payload, looking for known events. When a known event is detected, a log message is generated. Intrusion prevention systems analyze whole packets, both header and payload, looking for known events. When a known event is detected, packets are rejected. Next, let's go over the types of IDS systems. These include behavior-based and knowledge-based. Behavior-based creates a baseline of activity to identify normal behavior and then measures system performance against the baseline to detect abnormal behavior. This type of IDS system can detect previously unknown attack methods. Knowledge-based uses signatures similar to the signature definitions used by anti-malware software. It is only effective against known attack methods. Both host-based and network-based systems can be knowledge-based, behavior-based, or a combination of both. So the first network attacks we'll go over are denial of service and distributed denial of service. A denial of service attack floods a server with traffic, making a website or resource unavailable. A distributed denial of service attack is a denial of service attack that uses multiple computers or machines to flood a targeted resource. Both types of attacks overload a server or web application with the main goal of interrupting services. The principal difference between DOS and DDoS is that the former is a system-on-system attack, while the latter involves several systems attacking a single system. There are 5 main differences between DOS and DDoS attacks. 1. Ease of detection. 2. Speed of attack. 3. Traffic volume. 4. Manner of execution. And 5. Tracing of source. With ease of detection, since a DOS comes from a single location, it is easier to detect its origin and sever the connection. In fact, a proficient firewall can do this. On the other hand, a DDoS attack comes from multiple remote locations, disguising its origin. With the speed of attack, because a DDoS comes from multiple locations, it can be deployed much faster than a DOS attack that originates from one. The increased speed of attack makes detecting it more difficult, meaning increased damage or even catastrophic outcome. With traffic volume, a DDoS attack employs multiple remote machines, which means it can send much larger amounts of traffic from various locations simultaneously. This overloads a server rapidly in a manner that eludes detection. With manner of execution, a DDoS attack coordinates multiple hosts infected with malware, creating a botnet managed by a command and control server. In contrast, a DOS attack typically uses a script or a tool to carry out an attack from a single machine. And lastly, with tracing a source, the use of a botnet in a DDoS attack means that tracing the actual origin is much more complicated than tracing the origin of a DOS attack. Countermeasures for DOS and DDoS attacks include firewalls, routers, intrusion detection systems, intrusion prevention systems, disabling broadcast packets from entering and leaving, and disabling echo replies. Botnets, controllers, and bot herders represent significant threats due to the massive number of computers that can launch attacks. Botnets are a collection of compromised computing devices, often called bots or zombies. Bot herders are criminals who use a command and control server to remotely control the zombies, often use the botnet to launch attacks on other systems or to send spam or phishing emails. Denial of service attacks can take many forms and be used for various means. It can be to make a company lose business, to cripple a competitor, to distract from other attacks, or simply to cause trouble or make a statement. Denial of service attacks prevent a system from responding to legitimate questions for service. Common denial of service attacks include SYN flood attack, Smurf attack, and ping of death attack. SYN flood attacks disrupt the TCP three-way handshake. Smurf attacks employ an amplification network to send numerous response packets to a victim. And ping of death attacks send numerous oversized ping packets to the victim, causing the victim to freeze, crash, or reboot. Some more common types of denial of service attacks. So when dealing with network attacks, it is very, very important to know the order of the three-way handshake. It comes up commonly in discussions of TCP/IP-based network attacks. For example, the SYN flood attack exploits the TCP three-way handshake as follows. The attacker floods a victim site with SYN packets. The victim then responds to each SYN packet with a SYN ACT packet. The attacker does not respond with the last portion of the handshake, an ACT packet, leaving the victim waiting for a response. Then the attacker continues to send the victim SYN frames with a spoofed address. The victim then continues to attempt sessions with the attacker allocating resources to accommodate each of these inbound session requests. So many resources are allocated that the victim cannot process a legitimate inbound request for a TCP/IP session. Another type of network attack is called eavesdropping. Eavesdropping is simply listening to communication traffic for the purpose of duplicating it and or extracting confidential information. It's difficult to detect because it's a passive attack. Some countermeasures for this is to maintain physical access security, encryption in transit, and one-time authentication methods. Another type of network attack is impersonation or masquerading. This is the act of pretending to be someone or something you are not to gain unauthorized access to a network or system. Impersonation attacks also usually imply that authentication credentials have been stolen or falsified in order to bypass authentication mechanisms. Some countermeasures to stop this attack are one-time pads, token authentication systems, encrypting traffic, and employee awareness training. Some other type of network attacks are DNS attacks. DNS attacks include DNS poisoning and DNS spoofing. DNS poisoning is when an attacker alters the domain name to IP address mappings in a DNS system. They may redirect traffic to a rogue system or perform denial of service against that system. DNS spoofing is when an attacker sends false replies to a requesting system, beating the real reply from a valid DNS server. Some countermeasures for these attacks include allow only authorized changes to the DNS, restrict zone transfers, verify forwarders, and all log privileged DNS activities. Another type of DNS attack is a homograph attack. A homograph attack leverages similarities in character sets to register phony international domain names, also called IDNs, that appear legitimate to the naked eye. A way to mitigate this risk is to update your browser regularly. Also on the client side, modern browsers that use Punycode can stop it. On the server side, use policies implemented by ICANN. Another form of a network attack is hyperlink spoofing. Hyperlink spoofing is very similar to DNS spoofing. It can take the form of DNS spoofing or just simply be an alteration of the hyperlink URLs. It's usually successful because people just click